Gentlemen, welcome to the penultimate week of school and a new chapter. So this will be the last stuff we cover will be thermodynamics. I may throw one day in at the end on acids and bases. You won't even have a worksheet, just kind of as definitions. But thermodynamics is the study of energy that accompanies chemical reactions. In fact, thermodynamics is a study of energy that accompanies any change in energy. But thermodynamics within the realm of chemistry is the study of energy as it relates to chemical equations. This is also called thermochemistry. So energy energy change accompanies every chemical reaction. In every chemical reaction, there is a net gain or loss of energy in the chemicals. However, the energy of the universe is constant. Like the whole universe, energy is constant forever, always. It's just a constant amount. Energy cannot be created or destroyed. So the energy that's in the universe is in the universe, always will be, always has been. It's a constant. Now that's kind of true and kind of not. If you remember Einstein's most famous equation, which everyone knows and no one really knows what it means, E equals mc squared, where E equals energy and m equals mass. This actually tells us that mass and energy are the same thing. Mass is actually just a super concentrated form of energy. So it might be better to say that energy and mass of the universe remain constant, but we aren't going to be creating or destroying any mass either. So we can consider energy to always be constant. So when we talk about energy change, we're not talking about like the whole universe's energy changing. That's always constant. We're talking about energy going into or coming out of a specific area, and we define that area. We're interested in the energy that goes into or out of a certain chemical reaction, or into or out of a sample of water, a sample of matter, or something. And we define what we are measuring, what particular thing we're measuring, and that's called the system. And everything else in the whole universe is the surroundings. And we kind of put up this artificial barrier, and we say whether the system is taking in or giving off energy. So there are two basic types of chemical reactions and two basic types of energy processes in the whole universe. There's where energy goes out from the system into the surroundings. So energy goes from the system out into the surroundings. This is called exothermic. Energy is exiting the system. If the opposite, energy goes into the system, this is called endothermic. In endothermic, energy goes into. Endo, into, they're both exo and endo are both Greek, and they're pretty easy to understand. So energy going into the system. Now, something to be careful with about this, though. When energy is coming out of something, that's usually what we feel as warmth. So if I went to the lab and turned on a Bunsen burner, that Bunsen burner would get hot. The fire would get hot. It would be hot. And you might want to think, oh, that means energy is going into the Bunsen burner. No, actually, energy is coming off of it. Energy is coming off of those chemicals. In fact, it's coming off of the methane and the oxygen as they combust. And it's going into other things. It's going into us if we feel it closely enough. It's going into the atmosphere. But energy is coming out. So exothermic things generally, to us, feel warm. Because we're usually part of the surroundings. Now, if we define ourselves as a system, for instance, if you're, you decide to just test whether the pan is hot enough by shoving your hand on a warm pan. So you heat up a pan, you want to see if it's hot enough, and you decide, oh, I'm just going to test it by slapping my hand down on that. What's going on when your hand is being burnt is that energy is transferring from the pan into you. And if you define yourself as the system, that would be endothermic because energy is going into you. And if you define the pan as the system, it would be exothermic because energy is leaving the pan. Either way, probably a bad way to figure out the temperature of a pan. Though, we all make our own life choices. So exothermic and endothermic reactions. When we talk about chemical reactions, we're talking about the chemicals involved in the reactions. We say it's exothermic if energy comes out of those chemical bonds and out of those chemicals that are the reactants and products, and endothermic if energy goes into it. Some chemical reactions give off energy. Those are exothermic. Some chemical reactions need energy to begin, take in energy, and those are endothermic. So a little bit of how we measure heat, because in chemical reactions, again, energy is pretty much always going to be heat. Yes, there are other types of energy. There's kinetic, and there's mechanical, and nuclear, and all sorts of other types of energy. But in chemistry, we pretty much deal with the energy that is heat, which is basically kinetic energy at a molecular level or atomic level, how fast those particles are moving. So you may have noticed that some things heat up and cool down easier than other things. For instance, if you have aluminum foil and you heat it up, if you put aluminum foil on, say, over a fire and heat it up, if you take it off the fire, it'll be cool in almost no time at all. It heats up really quickly and it cools down really quickly. Aluminum is easy to heat up and easy to cool down. That would mean it has a low, what we call specific heat. And I'll get into that in a second. Water is very much the opposite. It takes a lot of energy to heat water. And by the way, that's where a lot of the energy that you eat and make goes. Your body is a lot water, and you have to keep it at a certain temperature. But it takes a lot of energy to heat water. And part of that is because the intermolecular forces in water hold that water together, and it's hard to get all those things, all those intermolecular forces kind of vibrating, breaking so that it can vibrate more. So water has a high specific heat. It takes a lot of energy to change the temperature of water. When water's temperature changed, it has absorbed a lot of energy. So this measurement of how easy or hard it is to heat something up is important for us to know, for us to understand exactly how much energy is going into or coming out of something. If you heat up a gram of aluminum by 1 degree, that takes way less energy than heating a gram of water by 1 degree. It just does. So to understand how much actual energy is going in or out, we have to compare how much energy it takes to raise the temperature of one substance versus another substance. And for that we use specific heat, which is abbreviated or indicated, it's not really abbreviated, but indicated by a lowercase c. So how much energy it takes to raise the temperature of 1 gram of a substance. So it has to be the same amount, otherwise that's ridiculous. It takes way less energy to heat up, a pot of water by 1 degree than a full Olympic-sized pool by 1 degree. But 1 gram of a substance by 1 degree Celsius or 1 Kelvin. So for thermochemical equations and all this stuff we're going to learn now, it actually doesn't matter whether you use Kelvin or Celsius, because we're talking about change in temperature, and 1 degree increase in Kelvin is the same as a 1 degree increase in Celsius. So you don't have to convert everything to kelvins like you did for gas laws. You can if you want, just make sure you report it correctly. So energy in the SI system is measured in one of two units. There are 2 units. They're still official, although I think they're going to try to move everything to joules, which is the second one here. Calorie, which you've all heard of probably because of, food. Calorie was originally the measurement of heat energy, how much energy it takes to heat things up. And a calorie is actually the amount of energy it takes to heat 1 gram of water up by 1 degree Celsius. The specific heat of water, it turns out, is exactly 1 calorie. That's how they defined it, as they did with a lot of the early SI system stuff. They defined it using water and other natural events. Now, it turns out that the energy that's heat energy is the exact same thing as the energy that's mechanical energy or any other type of energy. And originally they didn't know that, and now we do. Like, a calorie can be used to heat water, but it could also be used to push a piece of matter against gravity. So mechanical energy, motion energy, heat energy, it's all the same thing. Energy is energy. And once that was figured out, there's kind of been this shift to move everything to joules, which was originally measured to used to measure more mechanical things, like the energy something would have as it hits the ground if it falls from a certain distance. So this is a lot of the stuff you deal with in what kind of is called classical physics. When you take physics, you'll deal with it. So more and more, we're going to see stuff in joules, but both calories and joules are used. So you have to know the conversion factor. 1 calorie equals 4.18 joules. 1 calorie equals 4.18 joules. That's the conversion factor. Also, and this is something you're just going to have to know, and it's terrible, and I'm sorry about this, but there's a little c calorie, and then there's a capital C calorie, and they're not the same thing because, screw you guys, why make this easy? This is just terrible. But the capital C calorie is also called a dietary calorie, and that's what's labeled on food. So when you have a 3,000 a day calorie diet, you're eating 3,000 of the big C calories. And that's just 1,000 little c calories, or 1 kilocalorie, which is a perfectly legitimate word and entirely how the SI system was designed, so that's what they should call it. But be careful of the capitalization. 1 big C calorie equals 1 little c calorie, and that equals 4.184, or 4.18 joules. Sorry, you only need to go to the hundredths place for that. So that's how we measure energy going into or coming out of anything. So when we talk about how much energy we release when we burn a certain fuel. That's going to be in joules or calories, probably in joules. More and more often we're going in joules. And that's chemical energy, energy stored in chemical bonds being released in generally heat energy. But if you want to talk about how much energy it would take to push a rock of a certain weight, so let's say a 1,000 kilogram rock, a metric ton boulder, up a hill, and you have the height of the hill and the angle, and that would also be measured in calories. So same sort of energy. So when dealing with heat and energy, there's this one equation that you're going to keep seeing. And I have arranged it in the simplest way. A lot of times you'll see it arranged C equals Q over M delta T. I like arranging it in this way because there is no fraction in this. This is the easiest one to rearrange when you have to rearrange it. Q equals MC delta T. Q, lowercase q, of course, stands for heat. Everyone knows that. That's another thing in chemistry that just makes perfect sense. Just deal with it. M is the mass of the object in grams, and delta T is the change in temperature. So delta T, that triangle, that is a capital delta, and it means change in temperature. Well, with the T, it means change in temperature. So delta T is not two separate things, it's just one thing. The way you measure change in temperature is just that you take the final temperature and subtract from it the initial temperature. So if the final temperature is higher, you'll get a positive change in temperature, and if the final temperature is lower, you'll get a negative change in temperature, which makes sense. If something heats up, you would expect the change in temperature to be positive. If it cools down, you'd expect it to be negative. So this is the equation you'll be using to solve the basic problems that we'll be doing right at the beginning here. And I'm going to give you an example because it kind of is just like I'm throwing you this and throwing this at you, and you don't really know why we would use it or how we would use it. So here's an example: the specific heat of ethanol. And I'm going to label these as I go through. Again, this is something I like to do to keep straight so I don't screw things up. Specific heat is lowercase c of ethanol is 2.4 joules per grams degrees Celsius. So it could be in joules or calories, but it's always per grams degrees Celsius. This happens to be in joules. A sample of ethanol absorbs 676 joules of heat. Well, that would be your Q. That's the energy. Joules of heat, that's different than temperature. Temperature is how warm or cold something is. Q is the energy, measured in calories or joules. So just remember that heat isn't temperature. Heat is energy, and temperature is how that energy is reflected by how warm or cold something is. So the temperature rises from 22 degrees Celsius to 64 degrees Celsius. And we do not have to change that into kelvins because it's going to be a delta change, delta T. And it'll be the same in kelvins or in Celsius. We can see the temperature is going up. So this will be a positive delta T. I will actually calculate it, although most of you can probably do this in your head. So delta T equals temperature initial minus, temperature final minus temperature initial. Initial, so in this case, delta T equals 64 degrees Celsius minus 22 degrees Celsius, and delta T would, of course, equal 42. I hope I'm getting that right. I didn't use a calculator, and my brain is starting to go. So hopefully that's correct. 42 degrees Celsius would be your delta T. So what is the mass of the sample? So we're looking for mass, and we can actually figure that out. We can figure out how much ethanol is in that can or that jug or whatever based on all these other, based on knowing how much heat it absorbed, knowing its specific heat, and knowing the temperature change. So our equation is Q equals MC delta T. And again, I like this version of the equation if you're going to memorize it because it's the easiest to rearrange. If we want M by itself, we just take C delta T all down underneath the Q. M, divide both sides by C delta T is the other way of saying it. Equals Q divided by M, or divided by C delta T. Excuse me. And we have all these numbers. The mass equals 676 joules divided, and I will actually put in all the units and show you how they cancel out. I know you guys don't like going to that effort. Now that I've become, older and less likely to get stuff right without reminding myself about everything, I tend to do that because it helps me. But I You don't have to do that. It just keeps everything straight. So the specific heat is 2.4 joules per grams degrees Celsius, and then our delta T is times 42 degrees Celsius. Get rid of that dot there. And if you look, what happens with the units, and again, so this joules and this joules cancels, this delta C and this delta C cancels. And if I've mentioned before, if you have something on the bottom of a fraction, so a fraction and a fraction, this is actually just in the numerator. So it's just grams. That's what we have left. So our answer will be in grams, which is good because we want a mass. And then you just do the math. So really quickly, 676 divided by the quantity 2.4 times 42. Make sure you put that the two things in the denominator in parentheses, or the calculator will do order of operations incorrectly. Actually, it'll do it correctly as you told it, but incorrectly for what you want. And you will find that the thing weighs 6.7. Yeah, 6.7. I'm checking for sig figs, equals 6.7 grams. So you have 6.7 grams of ethanol. And that's your answer. And that's what you'll be doing in the first worksheet, just problems like that, and some basic conceptual stuff. Okay. Have a good day. Good luck this week. Again, only 2 weeks left. We'll get through it. See you, Jeff.